Okay, hello everyone. I'm Tina Sun, and today I'm going to talk about did the Central Arctic become a sediment-starved basin in the Quaternary. Arctic has always been a very popular spot for people for research. And here there is a program come in IODP's Expedition 302, which is Arctic Coring Expedition, ACEX. Its purpose is to rebuild the ancient sea ice data in Arctic Ocean, and the yellow square it is the sediment trap point, and the red circle is the core. In long-term sedimentation rate, the compare of beryllium-10 dating and biostratigraphic in multi-million year timescale in the Central Arctic was not sediment-starved. But what about in the Quaternary? First, we have to know what is sediment-starved basin. A sediment-starved place has three definitions. First is that the sedimentation rate scale is mm or cm per kilo years. Second is that there are very few terrigenous sediment supply into the ocean. And the third one is that it is usually thousands of kilometers away from the continent. A specific example of this sedimentation-starved location is at South Pacific Ocean Center. And next, we have to know what is MIS. MIS means marine isotope stage. It is detecting the various of oxygen 18. And when the oxygen 18's radio is low, it means that MIS is odd, which is interglacial period. And the same as the contrary is the glacial period, which is MIS is even. So now let's take a look at an ancient core, which is PS2185. Before 20th century, people used paleomagnetic dating, which is figure B, and we could see that here the bulk density, the beryllium 10, and the Planck formas, both the particle also shows that here is a peak at the glacial time. But there comes a difference, is that at 2001, someone discovered a coccolithophore named E. Huxley, which is this one. It discovered at the MIS table at 11 to 15, but this is something that should thrive at MIS 5. So scientists start to think that maybe their timetable was wrong. So now they turn into this timetable of MIS. But at 2023, there comes another question, is that another coccolithophore called P. lacunosa was found at MIS 7 here. But this one is something that should be extincted at MIS 12. So scientists now think that the sedimentation rate may be overestimated in the Central Arctic. Here comes our purpose. First is that we want to determine whether the beryllium-10 decay profile and biostratigraphic data from ACEX are compatible with classical paleomagnetic interpretations. Second is that we want to investigate spatial variety in sedimentation in the Central Arctic by sediment trap and changes in the correlative lithology unit. And question number 3 is that we want to outline how long-term changes in depositional rates should relate to sea ice persistence. Here is our method and material. First, we use the beryllium-10 dating. It is something that decay from the N2 and O2 after being hit by cosmic rays, like this here. And then it would decay into beryllium-10. Second, the beryllium-10 would stick on air and then goes into the ocean or under land. And they would decay into boron-10 by time, which is half-life 1.3 million years. Now we can detect the beryllium-10 and beryllium-9's ratio, so we can get the age of the sediment. The second method we use is OSL, which is obstacularly stimulated luminescence. We detect the crystal. When the crystal is buried under the ground, they would absorb energy, and we can detect the luminescence of the energy. And we have two ways to calculate sedimentation rate. First is nowadays. Nowadays, we can put a sediment trap into the ocean. This MAR is what we can get from the sediment trap, and SR is symbolized for a sedimentation rate. And the grain density and fractional porosity is a constant. The second one is how we count the sedimentation rate in the past. We use the beryllium ratio here, and we take the natural lag of it and put it into a depth. So we could have a slope. The slope means the sedimentation rate. And we have a rate of average, which is 15.8 meters per million years. And we have the other two, which have a twisted here. Between 1.1, 1.2, and 1.3, there is a boundary. And we would explain why we'd have a boundary here later. So if added with this boundary, we would find out that here the sedimentation rate is much smaller. Here is the result. We combine many different techniques and interpretations together. First, we could see the yellow circle is paleomagnetism. It is very much overestimated, like this. It is not on much of the line here. And second, we could see the beryllium-10 departed by time. Here, after time, they would departed much and much. And third is that the plantiform ramps suits the P. lacunosa, which the bigger one is here. Here is our discussion. So the first question is that, is Arctic a sedimentation-starved basin? First, we need to review the definition of sediment-starved. It is small scale, very few terrestrial sediment, and far away from continent. But we can look at the map of Arctic. The sedimentation rate we counted seems out that it is vary by special. Like here, it gets less into the center. And later, we found out that the Arctic has many territory input because it is an ocean that's surrounded by many lands. The third one is that the farthest is only 900 kilometers away from the continent. So we could get to a result is that the Arctic has not always been a sediment-starved basin. So if the Arctic is not always been a sediment-starved basin, why would we think that the Central Arctic as a sediment-starved basin? First, we can see that the map is here, and when it gets closer to the center, which is here, and the sedimentation rate would be much smaller, which means our core would be shorter. Like here, this time equals here. So when it is closer to the Central Arctic, we have the lower sedimentation rate. As the picture before, we could come out a picture like this. We can see that at the seasonal ice cover and marginal ice zone, we have a higher sedimentation rate. But under the perennial ice, we would have very small sedimentation rate. This is because of a paradox of sea ice. Sea ice can both increase and decrease the sediment can both increase and decrease the sedimentation. First is increase. The sea ice can be the sedimentation can be brought into ocean through the glacier. But when it comes to decrease, that is the sediment may be stocked in the ice or blocked on the ice. And now we can take a look at whether it is a sedimentation-starved basin in quaternary. We can see that at unit 1.1 and 1.3, there has a peak, like here. The peak means that it has a high variety of grain size, which means it has larger scales of glacier and would exist large ice shelves. And here, the twisted we talked about before is that we have a twist at 1.3 and 1.2 boundary. This twisted is because that here there is a very significant indicates that the sedimentation rate is changed in this boundary. And finally, we are going to talk about why is the paleomagnetic transition is incorrect so much. First is that no evidence shows that all planetary transits can be interpreted as chrome boundaries. Second is that there are the low organic carbon availability and high tide concentration may generate to a reverse chemical overprint. So here is our purpose. First, we want to compare the tools, and the answer is that the dating tools can't suit each other. And the second purpose is we want to build a spatial variety. So we can see that in margin ice zone and seasonal ice cover have more sedimentation rate. The third one is that a chronotary decline in the sedimentation indicated the expansion of Permian sea ice. So the conclusion is that first, Central Arctic. Okay. Okay. Okay.
I want to ask Krajan, how does the sea ice participate in transport and the deposition of sediment?
Okay, you are asking about. Uh, uh, okay, is it here?
Yeah.
Okay. The impact, the sediment when the sedimentation goes down, the increase is that the sedimentation may be brought into the ocean with the glacier like this. But the decrease is that when sedimentation comes from air, it could be blocked, or maybe when it comes after the glacier, it would float on the sea and cannot sink into the bottom of the sea to become a sediment.
Cause you showed two kind of photo. Like one is it shows they have a different. Wait a minute.
Which page?
In the front page.
Um,
Maybe. Yes. Wait a minute.
this.
Yeah. Like you show it is different. Like we thought it will start like at 5, but it show at 11 to 15. But like in another photo, it shows it it shows the difference in the like the middle is lower or higher than this one. So
I don't understand your question.
I am wondering which factor is influence the sedimentation rate the most, because I didn't hear very clear.
Which what?
Sedimentation, that I forget what it called, but which factor affects sedimentation rate the most?
Okay, I know you. Here, this one. This is seasonal ice cover, and this is marginal ice zone. So in this one, this one, we could see that more close to the Central Arctic, the lower sedimentation rate it comes, which is because of this. Because if it is near the continent, which is seasonal ice cover, it would change by season. And in the marginal ice zone, they would have higher sedimentation rate. But if it is under a perennial ice, which means persistent ice, it's forever. Okay, so they would have very small sedimentation rate.
Oh, so it's
So why did they show the different meanings of those kind of results?
You mean those bio things?
Yeah.
Okay. Here. May I move? Oh no. Okay. This is the timetable made by magnetic of Earth, and this one we discovered this coccolosophy here, and this one is which should have thrived in MIS 5, which is here, but now it shows here, which is impossible. So we rescheduled the timeline, and later the new timeline was wrong again, because at MIS 7 we found out something that should have extincted at MIS 12.
Okay, yesterday when I read this article, I was quite worried because this article was, as a geologist, I found it super complicated. I'm glad you made it, but still, you did a good job. You have tried your best, but you can improve a lot. Okay, so the first thing is go through this. So first of all, you talk about this ASEC. This is fine, and then here you started to talk about beryllium 10. I know you introduced later, but I think most of 99% of the students here, they don't know what is beryllium 10. Therefore, the best way is just to say different method, different dating method give different sedimentation rate. That would be good enough. Okay, here, to keep it simple, okay? And then I think what is missing is apparently here, there is a very basic method in this study, which is paleomagnetism, right? And it seems like the main purpose of this study was to say, okay, the sedimentation rate based on paleomagnetism was wrong. I think that's a key message. But then I think here in the introduction, you should use one slide to introduce paleomagnetism, because apparently this is the most basic method used in previous study, right? So you need to introduce paleomagnetism, and when I look at this is your page number. This is too small. And please, in the future, also for the audience, put it here or here, okay? Ideally here, you know the layout now. That would be audience, that would be the speaker, so put it here and make it large. Page number, and then there are several pronunciation issues such as terrigenous, and quaternary. And during your talk, you didn't use pointer at all. Use pointer next time. And look at the audience next time. You can do it. I think you spoke fluently, but you need to look at them. And here you introduce MIS. This is okay. I think this can be somehow followed by introduction of paleomagnetism. Okay, and you don't need this. You don't need this. You don't need this. You only need to say art means what, even means what. Okay, glacial and interglacial period. Okay, and this is from previous study, right? or this study, previous study? Previous study. Okay, so you can see that this is very busy. Okay, this is very busy. So, and also let's go to your purpose. You have too many purpose for a short talk. Okay, so if I were you, I would take out the third part. I will focus only on the first. You talk about the new data from beryllium 10 and the fossil, and then how they compare to paleomagnetic data, and then you talk about spatial variability. That's good enough. Don't talk about this. And then challenge in dating, this is good, but if I were you, when I present this, I will take away unrelated things such as this. I will make this part larger because the slide was too busy. Okay. And you know there's a typo from the author, 4 mass, should be 4 ans. And then beryllium 10, you introduce, then this one is nicely done, but you don't need to talk about this. In your later discussion, you didn't talk about OSL. So take it out. And this is very difficult, so don't talk about it. And, and you talk about the definition of sedimentation rate, this is okay. But I think it would be even better if you talk about why we should care about sedimentation rate in your introduction instead of its mathematic definition, its meaning, why we should care about it. And then you talk about the data already, but what was missing in your presentation is, I hope next time you can tell us, what is the sedimentation rate determined by paleomagnetism from previous study? And what is the sedimentation rate determined by beryllium 10? What's the difference? Because I can't see it here. Okay, you don't need to talk about this. Don't talk about this. Okay, talk about the importance of this parameter, sedimentation rate, instead of its definition. Then, okay, I think here you talk about the sedimentation rate difference, but you didn't give us a number. I need to know, okay, what's the sedimentation rate here? There's a number here. And what is the sedimentation rate here? How different they are. And then you talk about the spatial difference. This one is good. And this one is okay, although I feel it's a little bit busy, but it's okay. Then this one is nice. I know it's from the paper, but it's a really nice explanation of what is really going on. And this one is prepared by yourself. This is also really nice. I like it a lot. And this is too much. Take it out. I think this belongs to your topic 3. Take it out. And also take it out. Too complicated. Oh, this one is horrible. If you want to talk about the problem of paleomagnetism, put it to the introduction. You can talk about the problem. You see these curves? It's not a really diagnostic curve. So you can talk about its problem at the introduction. You can come to me if you have more questions, okay? Then conclusion, please make it short because you have a lot of content. Okay? Good. So I'm a little bit over time. So let's move on.